5 or 5.2 the correct channels and check on
knowing.
I'll just check.
It's different for each one.
What do you do?
I want you to keep this exposed if you can. That. Give me a clue when you want to start. I now call to order the Society's 2,410th meeting. In the 149th year since its founding on March 13th, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Brian Keating in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW's YouTube channel. Tonight is the 88th Joseph Henry Lecture, honoring the founder, first and longest serving president of PSW, Joseph Henry. We will therefore, after thanking our sponsors, begin with a few words about Professor Henry and tonight's use of the Society's ceremonial gavel. Thereafter, we will make a few announcements, followed by a reading of the minutes of the 2,409th meeting and the planet definition debate between Alan Stern and Ron Eckers. We will then turn to this evening's Joseph Henry Lecture, preceded by a short film on the subject of tonight's lecture, followed by a question and answer period. When the Q&A session is done, I will present two thank you gifts to our speaker, make a few closing announcements, thank those who make PSW possible, and adjourn the meeting to the social hour. First, please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who has asked to remain anonymous. And the sponsor of tonight's Joseph Henry Lecture, the intellectual property law firm of Millen White, Solano, and Brannigan, where I am a partner. In case you're curious. Tonight's lecture is the 88th Annual Joseph Henry Lecture, honoring PSW's founder, first and longest-serving president, Joseph Henry. Henry served as president of the Society from its founding in 1871 until his untimely death 7 years later in 1878. He was the preeminent American physicist of his time, an American Maxwell, and also perhaps the most prominent American scientist at that time. He is best known for his many contributions on electricity and magnetism, and for his finding that a powerful magnetic field is induced by flowing current through an insulator conductor round around a ferrite core, leading to the development of very much stronger electromagnets. His work on induction led directly to the invention of the telegraph and later to the invention of the telephone. In fact, Henry developed early versions of the telegraph and consulted with Samuel B. Morse, who ultimately invented the telegraph system that came to be widely adopted. Among his roles in founding and serving in many other institutions to foster science in America, Henry also was the founding secretary of the Smithsonian Institution. His death was headline news not only in America, but also around the world. And here in Washington, D.C., the city quite literally closed down to mourn his passing. We honor Henry today with this annual series of lectures on important topics of the day in science that would certainly have interested him. We also honor Henry today by using the Society's ceremonial gavel, carved from timbers of the White House, recovered during the Truman Reconstruction of 1949 to 1952. The timber used to make this gavel originally was part of the White House reconstruction of 1815 to 1817, after the British, those of the famous special relationship, burned it to the ground in the War of 1812, which should tell us all that former enemies can become very good friends. I am pleased to announce that the following new members have been elected to the Society. Miles Taylor, a philanthropist with Wellspring Philanthropic Fund, interested in environmental and climate sciences, paleontology, ornithology, and astronomy, who comes to PSW membership through attending the PSW Planet Definition Debate at the previous PSW meeting. Arthur Wood, a software engineer retired from CSC, interested in astronomy, who learned of PSW by attending a recent event. Todd Cranen, a video producer with Reason magazine, interested in theoretical physics, quantum mechanics, and cosmology, who claims his greatest achievement is that his mother loves him. And who comes to PSW through Meetup. And tonight's speaker, Brian Keating, whose background and interests will be clear to you, at least in part, from tonight's proceedings. Please join me in welcoming them to membership. All new members, and old members too, who haven't received one, are offered a copy of Volume 1 of the Philosophical Society of Washington, covering the period from March 1871 to June 1874, signed by me. Certainly a big attraction, I'm sure. And it tells you who the original members were, why they founded the society, and why they called it the Philosophical Society of Washington, as well as including minutes of early meetings of the society, which, interestingly enough, often address topics that concern us today. So if there's anybody here who's a new member, or is a member who never received a copy, please let me know. Come up and see me at the end of the Q&A, and I will be happy to provide one to you. Our social media director, Ann McLean, will now read the minutes of the 2409th meeting and the Planet Definition Debate between Alan Stern and Ron Eckers, delivered to the Society and guests on 29 April 2019. Ann is kindly filling in for recording secretary James Heelan, who is unable to attend tonight's proceedings. Ann.
Good evening.
On April 29, 2019, in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,409th meeting of the Society to order at 8:01 p.m. He announced the order of business that the evening's debate would be live-streamed on the internet and welcomed new members to the Society. President Milstein then introduced the debaters for the evening's planet definition debate. Ron Eckers, president of the International Astronomical Union from 2003 to 2006, argued in favor of the IAU definition. Alan Stern, principal investigator on NASA's New Horizons mission, argued in favor of the geophysical planet definition, or GPD. Arguing first, Eckers explained when the celestial body 2003 UB313 was discovered in 2006 and appeared larger than Pluto, the IAU needed to define whether or not it was a planet to determine which naming convention to apply to the body. That year, the IAU convened in Prague and through democratic process defined a planet to be an object in our solar system that orbits the sun, is surrounded by its own gravity, and cleared the neighborhood around its orbit. Because clearing the orbit focuses on gravitational effect an object has on other objects, the IAU definition is one of dynamics. By this definition, 2003 UB313 was deemed not a planet. So too was Pluto. In rebuttal, Stern advocated the GPD of a planet as a celestial body that is surrounded by its own gravity and has not undergone nuclear fusion in its interior, regardless of its orbital parameters. This definition is agnostic to the number of planets and applies to all planetary systems. Stern rejected the IAU definition as a product of non-expert consensus. Stretching the IAU's logic to the extreme, Stern said no solar system's planets meet the IAU's definition of a planet because none of them have definitively cleared their orbits. In reply, Eckers defended the IAU's requirement that a planet clear its orbit as one of practicality. The orbit of big planets around the sun are not significantly affected by the gravity of smaller objects around them, unlike Kuiper Belt objects that are in resonant orbit with the big planets. He added that a 2015 paper by Jean-Luc Margot showed the IAU definition is sound. Speaking last, Stern said the Margot paper showed that identical objects would be classified differently under the IAU's definition based solely on their locations in the solar system. Stern then highlighted a 2018 paper by planetary scientist Philip Metzger, which found that no planetary science research papers use the IAU definition, except for papers about the definition itself. The speakers then took questions from the audience. One member asked whether the geophysical planet definition would define moons as planets. Stern answered the GPD is not orbit dependent, and planetary scientists sometimes do refer to moons as planets. Eckers said the IAU definition is for the general public, who he says does not believe would accept defining moons as planets. Another member asked how the IAU addressed exoplanets. Eckers said the IAU definition was only for objects in our solar system and does not address exoplanets. Stern said there should be a single definition for planets regardless of their location. Following the robust question and answer period, President Milstein invited audience members to vote on the PSW website in favor of either the IAU definition or the GPD. When voting closed, the IAU definition received 30 votes, and the GPD received 130 votes. President Milstein then thanked the debaters, made the usual housekeeping announcements, and invited guests to join the society. At 10:05 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 13 Celsius. Weather, cloudy. Attendance in the Powell Auditorium, 132. Viewing through the live stream on the PSW Science YouTube channel, 367. Respectfully submitted on behalf of James Heelan, Recording Secretary.
Thank you so much, Ann. Do we have any comments or corrections on the minutes? Apparently not. Excuse me?
Motion to accept as read.
I didn't ask for the motion yet. Now I'm going to ask for the motion. Hearing none, do I have a motion to accept the meeting minutes as read?
Motion to accept.
Do I have a second? Second. All members in favor? Aye. All members opposed? The minutes are accepted as read, and they will be posted to the website in due course. It is my pleasure to introduce tonight's speaker, Brian Keating. Brian is professor of physics at the University of California, San Diego, where he is also director of the Axe Center for Experimental Cosmology, director of the Simons Observatory, and co-director of the Arthur C. Clarke Center for Human Imagination. Brian's research focuses on questions in cosmology, using optical, infrared, and microwave radiation detectors on state-of-the-art telescopes, in particular to see ancient light and discern the fundamental forces and fields that operated at the earliest moments of the universe. He pioneered the search for the earliest physical evidence of the inflationary epoch, the expansion of space in the early universe theorized to have occurred directly after the Big Bang, and he is a leading expert in the study of the cosmic microwave background, the universe's oldest light. He is an author on over 100 scientific publications, an inventor in 2 U.S. patents, and the author of the book, Losing the Nobel Prize, selected by numerous critics as one of the year's best science books when it was published. Among other honors and awards, Brian is the recipient of the Buchalter Cosmology Award and an elected fellow of the American Physical Society. Also recently, Brian was elected to the National Society of Black Physicists. Congratulations, Brian. And you told me something else that I should announce, because it's new here. No, what was it? Tell me.
Chair.
Ah, yes, he's now the Chancellor's Professor of Cosmology at the University of California, San Diego, which is an endowed chair. So please. Brian earned a BS in physics at Case Western Reserve University and an MS and PhD in physics at Brown University. Before we begin, Brian has provided a short film that he prepared, which is a good introduction to our subject. Whoops. That's you and me. Oh, okay. I don't know. Which one is it here? Didn't it work before?
There's no sound. It is the Cosmos Club system.
Yeah, well,
Yeah.
you'll have to read. It worked before.
Excuse me.
Didn't it work before?
Yeah. You rewired it right before you left.
Do you have the remote? The remote control for the sound system. It's not part of the film. It's mostly voiceover. I'll leave the answer to that question to Brian in the social hour. But for now, let's welcome Brian to the stage to talk about the beginning of all things.
This on? Good. What's that? Put underneath there. Well, thank you, Larry, for reading my introduction exactly as my mother wrote it for you. That was really lovely of you. It's a great honor to be here, and in all seriousness, thank you so much for all your graciousness and arranging this wonderful event for me at the Cosmos Club. What better place for a practicing cosmologist, not a cosmetologist, despite what you might think, to present this historic, august organization, founded 100 years before I was founded in 1971. So, and to be giving the Joseph Henry Lecture, one of my heroes in physics and in the world of experimental physics, which is what I characterize myself as, an experimental cosmologist. Not that I build cosmoses, I don't have that big an ego, but it is still part of my daily practice to use devices that Joseph Henry invented and concepts that he invented. So it really couldn't be a bigger honor for me to speak than I'm receiving tonight. So thank you all, Larry, the Cosmos Club, Robin, and Ann, and others, and then thank my UCSD friends and colleagues who also helped set this up, and Spira and others, many of whom would have liked to have been here because it dropped down to about 69 degrees in San Diego, so it's a little too cool for them. They'd like to be out here in the lovely humidity we have. Larry challenged me to come up with a talk title that would appeal to a wide audience of specialists, but also the general public. And he suggested, though, I use a very modest title, which is the beginning of everything. And I think it's not in any way modest, but the subject matter that I study, I think, is so fascinating, and it involves so many different aspects of fundamental physics, the pursuit of knowledge for its own sake. It may end up having applicability in making faster cell phones or things like that we care about in a practical technological sense, but that's not the reason we do it. And actually, in our field, it actually intersects more so with philosophy than any other subject in physics, perhaps. And it's fitting to be in the Philosophical Society, although I understand that the philosophical nature of the Philosophical Society is really natural philosophy, which is what they used to call physicist. And nowadays, physicists have a lot of derision for philosophers, and I'll talk about why I think that's a mistake, because I think philosophy is incredibly important to the motivation as to why we do what we do. I'm going to talk a lot about how we do what we do, what we do to do what we do, and I'm going to talk most intensely about the reasons why that motivate us as human beings to want to understand how the universe came to be, the beginning of all things. So this is a beautiful woodcut, the Flammarion woodcut called L'Atmosphere. And it was, nobody knows exactly how old it is. They've dated it to exactly somewhere between the 1500s and the invention of Photoshop. They're not sure when. This was actually a colorized version. The woodcut is actually black and white, of course. But it shows this figure, some say Galileo, peering beyond what he can see with his naked eye and using other senses, in this case teleporting and transporting his mind to the nether regions beyond what can be seen and glimpsed with the naked eye alone. And what's so fascinating to me about this is that the distant, old, faraway objects are so alien and different, cold and sterile, barren, versus the very verdant nature of what's close, new, fresh, and vibrant. And really, I think it's almost the other way around. When you peer back into the heavens, what you see is incredibly stimulating, and it's inspirational to people like me. And that may be, a sign of a certain psychiatric disorder I might have. But when I think about the earliest universe, the most large concepts that one could study, it really fills me with a great deal of satisfaction and awe. And I think that's even where the word awe should be best used. So the figure, as I say, we're not sure who that actually is or when it was actually invented. Whoops, I skipped one more slide. But nowadays, some of us peer into the heavens for another goal. And in my book, I candidly admit I was one of those folks that had their eyes on the understanding of the early universe, to be sure, and wanted to glimpse the origins of all things, but also had a secret desire, and for reasons I get into in the book, personal, related to individuals in my life, that motivated me to want to win the most prestigious accolade in all of humanity, which is the Nobel Prize. And I'm not going to talk too much about the Nobel Prize in tonight's talk. This is a wonderful depiction that Nature magazine did on the occasion of their review of my book. And it shows the South Pole, or what is supposed to be the South Pole, and it shows the telescopes down there. It shows some penguins, and penguins will come back in this talk, not just because we're all dressed up like penguins, but because penguins are the most mercurial and interesting, fascinating critters in the world. And if you come on the right night here and you can't decide on chicken or fish, you just choose penguin, okay? That's my recommendation to you. So getting back to heroes, so Henry was a hero, Galileo was probably my first hero as a young physicist, young astronomer. Some say he was the first physicist in that he was the first person to use tests, experimental tests of the laws of nature and philosophize about how those laws of nature could be explained mathematically. He was certainly the first observational astronomer, the first person to use a telescope. He didn't invent the telescope, but he unleashed its power on the heavens for the first time. And it's kind of surprising, it's as if somebody, Joseph Henry or Alexander Graham Bell, has this device, for communications, and all he does is use it to ask his butler to come downstairs and help him. Never thinks about what you could use it for beyond the simple application that it was originally invented for. So no one knows exactly who invented it, but they understand how Galileo came to possess this interesting tube, which he called the perspective tube, perspiculum, or spyglass. He did what all great academics do. He plagiarized it. He heard about the idea, and he copied it basically based on the oral description that he had heard from one of his friends, Paolo Sarpi. And this is in 1609. But what was amazing about Galileo is he could improve the telescope by his understanding of the laws of optics, a nascent field really in development only for a few years since the beginning of the invention of eyeglasses. Now, what was so interesting about eyeglasses, I learned in the writing of this book, is that eyeglasses were really invented, and the need for eyeglasses wasn't really apparent until after the invention of the printing press and the first Bibles were printed. Because until that time, there was no standard, the eye chart in the back of your optician's office or whatever. There was no such thing. There was no printed text that you could say, every person that can see this letter E from this distance has perfect vision, until the printing press. And what was the first thing that was printed by Gutenberg in the printing press? There were some pamphlets, but he printed a Bible. And what did Galileo's observations with a telescope, which was made from the same types of lenses by the same types of people, opticians, what did it use to overthrow? The Bible. It's amazing how interconnected the history is of this field of observational astronomy. And it continues to this day. So not far from here, 99 years ago, in 1920, there was a series of debates held, so-called The Great Debate. I claim in my book, according to Keating's taxonomy, which means almost nothing to anybody besides me and my close friends, I claim that was actually the third great debate. in a series of Copernican debates that are philosophical, appropriate for this organization. And that revolves around whether or not human beings are in any way central to the organization, makeup, composition, future or past of the universe. And there were 3 of these. The famous one held in April of 1920, a few miles from here, was over whether or not the Milky Way galaxy is the universe, or whether or not there are other galaxies like the Milky Way that also exist in the universe. Now we take it for granted, but it was only known back as late as the 1920s. People didn't know if the Milky Way was the entire universe. Galileo kicked this all off with that tiny little instrument. Only one tiny lens remains. That's at the center of that weird-looking object at the bottom there in the Museum of Galileo outside of Florence. And it's cracked. Unfortunately, it's cracked. And it's only about 1.5 inches across. But with this device, Galileo made revolutionary discoveries that had a tremendous impact both on his life, and some say it almost cost him his life, as I'll explain, but also on how human beings perceive our place in the universe. And we continue that tradition today. In Keating's taxonomy, we're now in the 5th great debate. And that consists of whether or not our universe is just one of an infinite possible number of universes called the multiverse. And I'll get into that towards the end. So this device kicked off a revolution, and what Galileo saw through this telescope, now we take for granted. But back then, it was a true revolution that people wouldn't believe even after they saw it with their own eyes. So this famous sketch at the top is really the one that kicked off the Copernican revolution, what I call the first great debate. It shows the planet Jupiter, this wonderfully illustrated circle. Okay, Galileo was actually quite an artist, and he was very good at sketching things. And he would not only sketch what he saw, but how he felt. He would exaggerate features and make scientific arguments by way of his sketch. So there's a real place in iconography and data science for the presentation of academic information in a way meant to manipulate and encourage people to understand your hypothesis and maybe subscribe to it. And so in Galileo's case, he sketched the planet Jupiter for several days in January of 1610. And during those several nights in January, cold, frigid, northern Italian nights, he noticed that the planet Jupiter was always surrounded by 4 stars. And they never moved, even when Jupiter was moving with respect to the faraway background stars. So eventually he realized correctly he was witnessing another solar system. He was seeing it on edge in the plane of the solar system. And the reason that the planets were alternating back and forth in a periodic fashion was because they were in orbit around the planet Jupiter. And that completely contradicted the notion that the Earth was the singular center of the universe, which was the solar system. And that's all really people thought the entire universe was. He also sketched the phases of Venus and showed that it looked like a little miniature moon. He sketched the planet Saturn. He didn't quite understand that Saturn's rings were not actually moons or a 3-planet system, as he originally conjectured. And then he sketched the surface of the moon as well, as shown here. Now, what's interesting about this book, for those of us that use refracting telescopes, such as myself, is that this book, if you will, was self-published. That's nice. And it was submitted without peer review, and that will come into play later on in a very famous event in my life that I want to get to. The other thing to note about this is it was published in Latin. And you're like, big deal, everyone in Italy speaks Latin. No, they don't, and they certainly didn't speak it back then. And this was the only way that Galileo was permitted by the Pope, Pope Urban, eventually Pope Urban, to publicize at most minimal impact. By publishing in Latin, he wasn't convicted at that time in 1610 of spreading the dangerous ideas of heliocentrism, which he started to promulgate. And in fact, the Pope would later say you can do as much research as you want as long as you don't teach it in Italian. So remember that. Sidereus Nuncius means the sidereal or starry messenger. It's written only in Latin. So he received critical acclaim. He became incredibly famous overnight. Within weeks, these discoveries made its way across the entire continent of Europe. Here he is shown with his funding agency, so his National Science Foundation, after whom he named the moons of Jupiter. It's funny, nowadays we name the telescopes after our patrons, in my case the Simons Observatory, but this would be like naming the moons, the National Science Foundation moons. These are the Duke and Duchess, and eventually these are the Venetian Doges in the Venetian Senate. And why is he showing it to them? They weren't near where he was in Padua and outside of Florence later. Well, he's showing it to them because they were a great military superpower. And what they really would have enjoyed at that time, as most militaries still enjoy, is a relationship between their best scientists and their best technology. So Galileo's first use of the telescope was, I call it mankind's second oldest desire. It was to make money. And the way that he did that is he sold it to the Venetian Senate. He said, look, fellows, mostly fellows, he said, look through this spyglass out onto the lagoon, and then come downstairs and see the boat that you saw way out in the distance in the lagoon. You could see that from the telescope a day in advance of when you'll be able to see it from land, from sea level. And they were mesmerized, because this basically would be like turning off the stealthiness of the stealth bomber. Imagine how much our adversaries would pay to do that. So that was exactly the most immediate benefit that Galileo sought. Well, this is 1610. And he did something remarkable that we as professors surely envy. And that was he got instantaneous tenure. So they promoted him to the University of Pisa. And more than that, they doubled his startup money. So that's a nice thing to have. They gave him twice his salary, and he was able to hire more people. Eventually, this would lead to his downfall. So, you out there who might not be tenured, you'll learn sometimes tenure is not all it's cracked up to be, because getting tenure put him within the reach of the Catholic Church. And I'll get to that in just a second, of course, the famous story of Galileo's downfall. So he had great critical acclaim, and he had great popularity. He was on a book signing tour for a long time. These copies are now mostly unavailable, actually legitimate copies. Very hard to find legitimate copies. But then he made a fatal hubristic overstep. And that was in his publication of perhaps one of the most important books of all time, called The Dialogue, or the Dialogo. And in it, he conveys a debate, just like you guys had a debate last month. Except it wasn't over the debate of a planet, is Pluto a planet, basically, and or not. And that was a heated debate. I'm glad I missed that one. I don't want to get too anxious. But in this book, he had a dialogue between three people, but really only two are important. One is named Salvati, which conveys the sense of salvation or savior, the brilliant man whose intellect outshines the astronomical objects of which he describes. Brilliant. And those were Galileo's arguments. In the mouth of the character he called Simplicio, which translates into the simpleton, he put the mouth of the Pope. The arguments for geocentrism, that the Earth is still the center of the solar system. And those of you in the audience who maybe don't speak Latin, or nobody speaks Latin, that's kind of a dumb thing to say, but you might speak Italian, and you'll note this book is written in Italian. So what did he do? The Pope told him no more publications unless you publish in Latin. He published this in Italian. Everybody could read Italian. It publicized these discoveries of heliocentrism, which had been placed on the index of banned prohibited books. This was a huge tactical overstep for such a brilliant scientist, and it led to his downfall. So in what I call the Great Debate, the first one, he was promoting, using telescopic evidence, the notion that there are multiple centers to the solar system. He did not prove that the sun is the center of the solar system. That wouldn't come for more than 100 years. So nowadays I get questions, I go on radio shows sometimes, people call up and say, well, I think the Earth is flat, can you prove me wrong? But yeah, I challenge people, it's relatively simple to prove that the Earth is not flat, but can you prove that the Earth goes around the sun? I bet very few people in the audience can actually do that. I usually use that when there's a graduate student that I'm not ready to yet graduate, and I ask her to answer that question. No, I'm just kidding. I don't do that. I'm not that malicious. So this overthrew that, and eventually it would be accepted that the theory of geocentrism was wrong. And along the way, of course, Galileo got into a bit of hot water. Here he is appearing in front of the Holy See, which I think is kind of ironic, in that the sea is like they get to see things, but they don't want to look through a telescope, right? That's too much looking for them. In this case, he's appearing in front of his friend, that's Urban. There's a guy with a big stick, looks like a conquistador, and they're threatening, if you don't recant your discoveries, self-published discoveries, we're going to put you in, either kill you or put you in lockdown. And he wisely accepted lockdown, although under his breath he's rumored to say, and yet the Earth still moves. And I know a lot of smarmy academics who would do the same thing, but of course he ended up getting imprisoned. And the prison was kind of a white-collar criminal place. It was only about a mile away from where his daughters, his illegitimate daughters, lived outside of Florence, a beautiful place. I actually hosted a conference there a couple of years ago describing the same types of relativity studies that we do today and relating them to the first scientist, Galileo, that studied relativity, the physics of relative motion. And it was just titanic, the things that he did in this great book. So what Galileo saw through his telescope extended to the realm of the planets, and eventually to the realm of the nebulae in the terms of actual clusters of stars, of gas, of dust in the Milky Way galaxy. He wasn't able to see beyond the Milky Way galaxy, as we'll get to, and those came in the next great debate. So after about 100 years later, the next great scientist to take the telescopic baton from Galileo was a man in England named William Herschel. Herschel developed an enormous telescope. It was about 1 meter across and about 10 meters long. It was called the Leviathan. And through it, he made a map of the Milky Way galaxy, among many other things, with great assistance from the first woman scientist, the first woman who's credited as being a scientist in the Royal Society, Caroline. They discovered a great many phenomena together, and he called her his secret weapon, and without which he would not have made the discoveries that he did, one of which was a blunder. And that was to show, in his mind, his observations showed the Earth is located around the sun. Everybody knew that since Galileo. But that the Sun-Earth system was located near the center of the Milky Way galaxy, which is wrong. But the reason that he was wrong owes in part to this desire to center humanity's existence and importance on us, and that we are somehow central to the orchestration of the universe. It's a compulsion that is psychological in nature, presumably, but makes people overestimate or overreach in their ascribing their weight to their data. And that continues to this very day, in a very dangerous aspect of how modern science is done that most scientists don't like to talk about. But I'm okay talking about it. And luckily, I've made a lot of blunders, so I have a lot of material to talk about. So he put us at the center of the Milky Way. The reason why comes down to dust. Might not seem important, but dust is perhaps the most important substance in the entire universe. So those of you who read books, as I do, in bed sometimes, and they're hardcover, the book jacket is my nemesis. I used to hate the book jacket. Falls off, gets on the ground. And what's another name for the book jacket? The dust jacket. How much dust is falling on people's books? Is it like in the middle of like the Sahara, waving it around, reading? No, but actually dust, I came to realize through the telling of the story, is ubiquitous, important, essential to the makeup of the universe, and in fact to our own existence, as I'll demonstrate later. So what caused Herschel and also Galileo to stumble and make errors of overestimation? Dust. So dust diminishes the intensity of light as it travels throughout the cosmos. It scatters away the photons that would otherwise reach your telescope unimpeded. And in doing so, you would impute to greater distances the objects you see through your telescope. So as long as there's dust in the universe, as shown here, if you're looking at a street light through a dusty window versus an open or clean window, you would impute a greater distance to the object on the right, even though they're at the exact same distance. Dust does other things, but that's the most important thing that it does in the context of why Herschel overestimated, if you will, the centrality of the solar system within the Milky Way. So it's actually like you're a pilot inside of an aircraft. You ever been inside of a cloud when you're flying across the country? When you're in a cloud, if you're in a cockpit, when you look around in any direction, it seems like the cockpit is the center of this sphere, a fictitious sphere. And pilots in the audience might know that. We call it like sitting inside of a ping pong ball. That's the sensation that you get. Well, the Earth is also sitting inside of an object that scatters and deflects and diminishes light as it travels throughout the cosmos, and that's dust. I'll explain the origin of dust later. I've actually brought a piece of dust with me, aka a meteorite, and I'm going to present it to Larry in the back as a gift and of gratitude for having me here, but I'm going to use it as a prop as we go on. So dust diminishes the intensity of light traversing the cosmos. It's ubiquitous. It's throughout the entire universe. Now, in this image, we show the actual place of where the cosmos is located, or our galaxy is located. You see the sun is closer to 2/3 of the way out on a spiral arm in the galaxy, very far from the center, actually. It was, in terms of, I like to quote it in terms of miles that Herschel was off from being accurate, but I won't do that. He was off by, almost 20,000 light years in his estimation of where the galaxy was centered. And that's okay, and we wouldn't know until many, many decades later where the Earth is actually located. And that was concomitant with what I call the third great debate, but you all, every day when you talk about this, call this the great debate. This was held on April 26th, starting in the Smithsonian Museum, which I understand Professor Henry had a great attachment to as well. And it concerned the nature of these two different phenomena, or apparently similar phenomena, but there seemed to be some relations that made them similar in appearance, but they couldn't be the same thing, or so certain astronomers thought. So when you look through a giant telescope, you would see these objects, and they were called either nebulae, in the case of, that's the Orion Nebulae on the side, and the other side, sometimes they were called spiral nebulae. But it wasn't clear to the astronomers of the 1920s, this wasn't solved in 1920, whether or not there were nebulae like the nebulae I show somewhere in this picture here. Reflection nebula is down over there on the lower right. That's just an example like the reflection nebula of the Orion Nebula, or whether they were part of the galaxy, or whether they were far, far away from our galaxy. That was the great debate held in 1920, 100 years ago, next April. So we should celebrate that. It actually wasn't resolved for many years, until a very famous astronomer who went on to have a telescope named after him by the name of Edwin Hubble, who never won the Nobel Prize, mind you, but that's okay. That's not the only thing that counts in life. He claimed that these objects were far, far away from the center of our galaxy. And the first one he turned his eyes to was an object that you can see, not tonight, because it's too cloudy, and it's also mainly visible in the fall. But this is the Andromeda Galaxy, or back then it was called the Andromeda Nebula. This, today we know, lies at a distance of about 3 million light years. So light that Hubble was seeing, or that we would see if we could see it in a couple of months when it emerges from behind the sun. When we see that light set off when Lucy was walking around Olduvai Gorge in Africa. When you think about how ancient these photons are, photons don't age. They're like Hollywood miracle secrets, that you'll never get old if you're a photon. And of course, the only way that they have to keep traveling. And so the famous joke of why photons don't bring luggage is because they're traveling light. Okay, that's a bad one. Okay, I didn't break out my joke about planets. Okay, fine. How do the solar system astronomers decide to have a vote? They plan it. Okay, I can go all night, but I won't. Okay. Getting back to reality here. Hubble looked through his telescope on Mount Wilson and actually held this plate in my hand. This is a plate that was made in 1923, again, almost 100 years old. And on it, he's got these letters that he wrote down, and that stands for nova. And then at the top, he writes down an N, and then he X's it out. I was lucky enough to print this in color in the book, because otherwise you can't really capture the excitement. He wrote Ver. And he discovered as a variable star called a Cepheid variable, which is a very famous type of star, thanks to an astronomer by the name of Henrietta Swan-Leavitt, who made these pioneering measurements that showed you could use these variable stars as the longest ladders in the universe. She did that. She gets very little credit for it, and what we call Hubble's law, in some sense people think should be called Leavitt's law, and the relation between the period and luminosity of these objects is actually to be known as Leavitt's law, properly so. Now, what caused Hubble, famously, he overestimated the distance to this nebula or galaxy, and that was due to the effects of our best friend dust. Because what dust does is diminishes the light, making you think things are farther away, and it does something else. It also makes light appear more red. And you can see that when there's a sunrise and a sunset appearing very red, and then at noon, when the sun's directly overhead, it appears yellow. But the sun doesn't change its temperature between noon and sunset, say. But what's going on is that there's more dust that the sunlight is traversing in the Earth's atmosphere. When it's along the horizon, a longer optical path length. Same thing happens in every galaxy. This is a Spitzer Space Telescope image. And Lyman Spitzer was a famous astronomer at Princeton, where Joseph Henry was. And his son is named Nicholas Spitzer, and he's a colleague of mine at UC San Diego. A phenomenal biologist, and he tells stories about going rowboating with Einstein with his dad, and just amazing connections between us at UCSD and these great astronomers and physicists of the past century. So dust diminished, and it made things more red, and that caused Hubble to overestimate this distance. So it was actually closer than he imputed there to be. But because the Hubble constant is related to the age of the universe, and I know you've had lectures by my friend and Nobelist Adam Rees here, who uses the properties of Cepheids and other objects in the same way, the first thing he does is correct for dust, the effects of dust, because it makes objects appear more red. And for the aficionados in the audience, the photographs that these things were printed on were photographic emulsions that are less sensitive to red light than to blue light. That's why anyone ever been in a dark room here that's not over the age of 50? Anybody? Yeah, okay, good. So what color is the light in a dark room? Red. Because the photographic emulsion is less sensitive to red light, you won't expose it. That meant when he tried to expose the red light of a star, it didn't appear as bright as it actually is. Because dust had made it redder, photographs are less sensitive to red light. Another reason he overestimated the distance. He thought it was farther away. But that's okay. Eventually things were resolved in Hubble's favor, and we came to an understanding that the universe was evolving, that things in the universe were moving away from each other. And you've had many lectures on the Big Bang. I'm not going to get into too much about the Big Bang itself, other than to say that the Big Bang may not have been that big, and it may not have banged at all, in a sense that I'm going to get to. And the question of what actually happened at that moment of banging, if indeed there was a moment, is the most crucial question in cosmology. And it really builds upon the previous great debate, is informing our current great debate. So this became the fourth great debate. Is the universe eternal, static, unchanging? That's called the steady state model. Or is it dynamic, evolving, moving like a minor planet? No, is it expanding away? Everything's separating more and more over time. And later, it's shown to accelerate in its expansion. So there was a great debate, and this was over whether or not the universe is eternal. And eventually, the Big Bang model won out. But as often happens in science, you discover something new for the first time. Then you discover, well, there are problems with what you discovered in that first thing, and you have to explain it by conjecturing another solution that solves that. Well, that thing has its own problems, and so on and so on and so on. That's what makes science so interesting, but it's also predicated on the fact that there is no sort of absolute knowledge that you can have. Isaac Asimov once said something to the effect, if you think that the Earth is flat, you're wrong. And if you think the Earth is a sphere, you're wrong. It's not actually a perfect sphere, right? But if you think they're wrong in exactly the same way, then you're a fool, because one is much more accurate than the other. And so that's a little bit of science philosophy here. But this was a really great and puzzling notion. So great, famously, Einstein thought the universe was static and was only convinced after Hubble showed him his data on the Cepheid period luminosity relationship and so-called redshift distance relationship, the Hubble's law. And that convinced him, and then he later apocryphally, we think, said it was my biggest blunder. So even the great Einstein thought that the universe was static. And everybody thought that for 2,000 plus years, back to Ptolemy, Aristotle, etc. And so it was natural to have that preconceived notion to only look for things that comport with your prevailing hypothesis. And scientists are as prone to this type of phenomena called confirmation bias as any other individual that I know, maybe more so when other things get thrown into the mix, like shiny gold medallions. But again, we're not going to talk about that. I'm not bitter. No, I'm just kidding. So the question of what banged, what began, and how big was it was the subject of the fourth great debate. Now, there was a notion that couldn't be really held after the discovery of Hubble, which was that you couldn't say the universe was static. You couldn't say it was unchanging. It was obvious the universe was changing, and there were many lines of evidence that showed it was changing, but it wasn't possible to exclude the fact that it may have evolved in a series of cycles. Big crunch, big bang, big crunch, big bang, and in that sense be countably infinity to the past. In other words, the universe could be infinitely old, but just having a series of cycles unending in time. And that was the notion of the quasi-steady state universe. So you're literally adding epicycles on. This is in the 1950s. Fred Hoyle, Jeff Burbidge, my late colleague at UCSD, and many other eminent scientists maintained that the universe was a periodic series of collapse and rebirth, kind of a phoenix rising from the ashes. But soon after the discovery of the field of study that I engage in, which is the cosmic microwave background radiation, this was discovered in 1965. These two radio astronomers were working at Bell Labs. They were trying to communicate with the Telstar satellite, which was the first satellite communication system ever launched by the United States in the early 1960s. They were looking up at this satellite, and famously, they couldn't get rid of this persistent hiss of radiation that seemed to come in all directions, no matter what time of day, no matter what time of year, and no matter which direction they looked, even when they pointed at New York City. So they pointed at New York City. This is from New Jersey, okay? It's probably the best thing that ever came out of New Jersey. Just kidding. I'm a New Yorker, okay? All right, so they looked towards all possible sources of what's called systematic error. Famously, they found a family of pigeons living inside this 7-meter diameter antenna. And they said, well, these pigeons are depositing a white dielectric material inside of here. Let us drive these pigeons down to Philadelphia. I'm not going to say anything about Philadelphia, some of my best friends live there. But they drove it down to Philadelphia. Now, these are pigeons. What are pigeons known for doing? Homing. They returned, they kept coming back, and finally, Arno Penzias had to get a shotgun. And he said famously, the pigeons disappeared in a little bang, and we discovered the Big Bang. I would have liked to have seen that NSF grant request. Yeah, we need a shotgun to kill these sources of systematic error. And of course, they famously won a Nobel Prize, the first Nobel Prize in cosmology. See, cosmology wasn't considered physics. Even astronomy wasn't considered physics. Arguably, the Nobel Prize for the discovery of the accelerating universe, won by my friend Adam Rees and Brian Schmidt and Saul Perlmutter, that was the first observational astronomy Nobel Prize ever won, and that was in 2011. So astronomy wasn't considered part of physics, and that explains why Hubble never won a Nobel Prize, at least, for those of us who care about such things. But the first one for cosmology wasn't afforded until 1978, because cosmology was described as a science wherein the practitioners were often wrong, but never in doubt. We kept changing the age of the universe. Sometimes it was found that the age of the universe was younger than the age of the Earth. It's kind of like finding out you're older than your dad. It's kind of weird, freaky, okay? But anyway, cosmologists didn't become an actual practical, precise science until this discovery, when they measured the famous 3 Kelvin, actually 2.726 degree above absolute zero microwave background. And then for almost 3 decades, astronomers kept peering into the microwave background, trying to see if there were any anomalies, any imperfections in it, any notion of why the universe could be evolving from such an enormously smooth and practically impervious surface, the so-called surface of last scattering, which is smoother than the billiard balls on the 3rd floor here, by the way. In other words, if you take the average radius of a billiard ball, compare it to the instantaneous radius, the fluctuations are about 10 to the minus 4. The fluctuations in the microwave background were only found to be about 1 part in 10 to the 5 in 1992, as I'll show in just a second. That brings up a big problem, and it's a big problem that even Isaac Newton realized. He said, in an isotropic universe that's completely homogeneous, it's the same everywhere, it looks the same everywhere, perfectly smooth, there's no place to tell a blob of matter to accrete and accumulate and form a planet or a star. What breaks the tie in terms of gravity in order to tell matter to accumulate in one place versus another? This was a foundational, fundamental flaw in the Big Bang theory. The uniformity of the microwave background was too smooth, it seemed, to produce the matter and structure that allowed us to exist to ask the question, why is the universe so smooth? And this was a big problem until 1992, when the COBE satellite produced this image, or an image, this is actually the WMAP satellite version of this, a later image of it. And this shows the level of fluctuation is just a few parts in a million, or a few tens of parts in a million. In other words, the average temperature at any point, if you have microwave vision, you look out at the microwave sky, it fluctuates by only 1 part in 100,000 at best. And that's smoother than, I say, than a billiard ball, which we think of as pretty smooth, except when I'm playing. I make big dents in billiard balls. Don't let me upstairs. So how did these fluctuations get there? Remember, constant theme. You explain something new, then you find problems in your new explanation. Even though it's an improvement, it still has things that seem really puzzling and paradoxical. And you wash, rinse, repeat. That's what you do as a scientist. So this is what inspired me in 2001 to create what would later be called BICEP and BICEP2. This is an instrument to understand how did those fluctuations in the upper right get imprinted in the microwave background that led to overdensities in the amount of energy and matter that could seed the galaxies shown there. That's the Hubble Deep Field, a section of the Hubble Deep Field. So how did you get from almost pure uniformity to huge amounts of clumpiness, billions and trillions of times fluctuations, not just a part in 100,000? Well, in 1980, a scientist by the name of Alan Guth came up with a theory that could potentially explain how the fluctuations were laid down at the earliest moments of the universe before the Big Bang. You shouldn't think of the Big Bang as time equals 0 necessarily. It could be, but what we really think about and we talk about when we talk about the Big Bang is everything that happened after the formation of the first elements in the universe. Hydrogen, helium, etc. Lithium. It's more important for some people than others, but at any rate, the fluctuations in the microwave background were theorized by Guth and colleagues to have originated from a very mysterious exotic field, a quantum field a scalar quantum field for you aficionados called the inflaton. And that ignited a period of an exponential inflation that lasted for the briefest of moments, for only a trillionth of a trillionth of a trillionth of a second, and yet planted the tiniest seeds from which these enormous sequoia-like fluctuations in the amount of matter, energy, and radiation would later sprout. It's a beautiful description. It puts the spark, it puts the answer to the question of what ignited the Big Bang. It's a phenomenal idea, but it was unproven. And it seemed for a while it could not be proven until one day it was proven. And I'm going to tell you what happened next. But of course, then this is related to what I call the fifth great debate. Because, and I won't talk too much about this, but just as there are many planets, and Earth, as you found out last month, there are many, many other things that could be planets. Some things aren't planets, whatever, you win some, you lose some. Let's say there's 10 planets per star in our galaxy. There's 100 billion stars in our galaxy. That means there's a trillion planets or planet-like objects, and they have a trillion debates going on, throughout the universe probably. But in that case, that's just our galaxy. Now, what if I tell you there's there's at least 100 billion galaxies just like this image here, distributed throughout what we call the observable universe. And let's say each one of them has a trillion planets. It has 10 per star, 10 times 100 billion is a trillion. So you have a trillion galaxies, each one with a trillion stars with the planets surrounding them. It's just an enormous thing to think about. But the next extrapolation is say, what if there's a trillion universes? And it turns out that's an exact, unavoidable, inescapable extrapolation from the theory of inflation. You cannot have an inflationary universe in most scenarios and avoid what's called the problem of the multiverse. So when we were kids, the universe was everything there is. But now we have to think of space-time as being everything that there is. And within it, universes pop into and out of existence in this scenario called the multiverse. This has graver consequences for philosophy, and some even say theology, than any of the Copernican great debates that I've described so far. The stakes could not be higher for science, and the meaning of science in a multiverse is one that is greatly debated to this very day. So what have we learned up until this point? This is sort of the background theory behind the experiment. Now we're soon going to go on a voyage to the bottom of the Earth, so stay awake. If you look out, you first saw the planets and the nebulae that Galileo saw. Then you see the galaxies that Hubble saw. Then you see the clusters of galaxies that the Hubble telescope saw. And then you see nothing. That's called the cosmic dark ages. That's this talk in and of its own right. Then you see the CMB, my favorite thing to study. And then before that, very little is known. Very much is known about everything that happened after the CMB, and even after the first nanosecond. But physicists don't think of things in terms of linear time. We don't think about, well, the difference between 2 seconds and 1 second is the same between 1 second and a nanosecond. No. The physics that operates at those times and at those energy scales is vastly different. It couldn't be more different. It's not a billionth of a second is the same as zero. It's far, far different than that. We want to understand what happened a trillionth of a trillionth of a trillionth of a second after the Big Bang. If inflation took place, that's what would describe how the universe evolved from that point. So we wanted to understand this, and in order to motivate and see if we could find evidence for inflation, that would be the so-called smoking gun that inflation took place. And it turned out there was a type of prediction made by a Russian colleague of mine and later on colleagues of mine in the US, Alexander Polnarev, and then physicists in the US and Canada, predicted that if inflation took place, there would unavoidably be waves of gravity permeating the universe, suffusing the entire cosmos. And if that were true, and gravitational waves like light travel at the speed of light and endure forever, then some of those photons would be around at the time the CMB was produced, the cosmic microwave background. And if that were true, they would shake up what's called the polarization of the microwave background in a uniquely predictive way. And that came to be called B-mode polarization. Not the greatest name. I won't get into why it's called that. And that B-mode polarization became my fixation. It became the very thing that I most wanted to detect in life, because in doing so, it would prove that inflation took place. And if inflation took place, the multiverse is true. It couldn't be a bigger thing for a scientist to study. And I would win one of those shiny medallions. So how do you do it? Well, the answer rests on something that should be more familiar than it is. It's the third important property of light. It's called its polarization. So those of you who have been favored enough to visit UC San Diego and go out to the beach, you may have been advised to bring with you some sunglasses. So you see some water waves on the top there, and they're kind of light and dark, and they're coming towards us. And you can actually use the properties of water and its waves. You can learn about how the water's depth is, what its salinity is even, by making use of what's called polarization. So light has three main characteristics: its brightness, its frequency or color, and its polarization. So if you look at those ocean waves I showed in the previous slide in La Jolla Cove, light comes from the sun. It's unpolarized. It's oscillating in all possible directions. It bounces off the surface of the ocean, and one of those polarization states gets suppressed. The other one then is relatively enhanced, so you get a certain amount of horizontal polarization reflecting off the Earth's ocean surface. And then polarizing sunglasses work by suppressing that amount of polarization that's reflected. Because actually you don't want to see the reflection. That's what we call glare. So if you ever put a circular polarizing filter or a linear polarizing filter on your camera, you've noticed this, and I brought with me my standard San Diego sunglasses to demonstrate this. The notion to keep in mind is that when light interacts with matter, it produces polarized light. Inverting that, you can tell the source of the light, and you can tell the surface of the scattering where it took place. You can learn about that using polarization, as I will demonstrate. So light coming from that projector bounces off a mirror, and it's incandescent, it's unpolarized. And so it bounces off just like bouncing off a mirror. And if you look through these glasses at this orientation, it's suppressing one of the orientations of polarization. If I rotate 90 degrees, you see the color changes, and now it's green. Well, it changes 2 times for every physical rotation of the glasses. So it started off, it was purple, and that's just from the suppression of the color that's polarized vertically. Then it goes horizontal, and it becomes green. Then it's purple, and it's green again. So you can identify a source of polarized light with polarized sunglasses, and rotating your head once around, the light will go through 4 periods of intensity modulation. That's the hallmark, the imprimatur of polarization. And that's what we did, not using an optical telescope like Galileo had, but we did it with a microwave telescope whose design I'm now going to show. So this shows the interaction of light with an electron, producing scattering light that's 100% polar, can be 100% polarized. And then the type of swirly twistiness that you see in the sky can be broken down into 2 classes, one called E modes and one called B modes. Suffice it to say that B modes, as shown above, come only from gravitational waves. We think that would be the main source of gravitational waves. Remember what detection of gravitational waves would mean in the CMB. Remember how big a deal it was for LIGO a couple of years ago. That was just 2 puny black holes crashing into each other, 30 solar masses each. Think about all the mass, all the energy in the solar system, in the universe, in the entire galaxy, everything exploding forth, not in a millisecond, but in a trillionth of a trillionth of a trillionth of a second. Think of how much more gravitational energy is associated with such a process. So again, detecting B modes means you detect gravity waves, gravitational waves. You detect gravitational waves, it means that inflation took place. You detect inflation took place, it means we live in a multiverse. That's the way I conceived to do this experiment called BICEP. So BICEP differs from Galileo's telescope, not so much. It has lenses, 2 lenses, one located near your eye called the eyepiece, one located closer to the object, the objective. And instead of focusing onto Galileo's retina with trillions of cells that can detect light and dark, colors, etc., we detected microwave polarized light using these transition-edge superconducting detectors. These are magical sensors that when you cool them down to below 1 Kelvin, 1 degree above absolute zero, are the most sensitive detectors of microwave energy like that in the CMB ever invented. And later on there'll be a connection to Joseph Henry, if you'll bear with me when I describe the Simons Observatory. Instead of lenses made of glass that cracked in half, microwaves are transparent, go transparently through this polyethylene material that's shown on the right, same material used to make milk jugs. So it's not that exotic, it's not that big. It's a little bigger than Galileo's, and it's a lot wider because the wavelength's much, much longer, but practically it's the same. Galileo had another innovation. He put the telescope on a tripod. If you ever look through a telescope and not had it on a tripod, it does 2 things. It magnifies the apparent rotation speed of the Earth by the magnification of the telescope, and it magnifies your wobbly hands as well. So we also need a mount like Galileo used, and we have a mount that's about 10,000 pounds of steel, and yet can pirouette across the entire sky in a few seconds and park and steer and point within a few arc seconds. Just phenomenal accuracy and precision of this wonderful device. I would have loved to do this experiment from San Diego. You saw how glorious it is. That was a bad weather day I showed you before in San Diego. And instead, we had to take it to the bottom of the planet. We took it to Antarctica for the following reason. Antarctica, by the average temperature and the average elevation, is the highest and coldest of all 7 continents. Now, why is that important? Well, when things are cold and dry, there's less water vapor in the atmosphere. This telescope would be best located in space, but a space telescope costs 100 times more than a ground-based telescope. The launch costs, et cetera, included. So instead, we take it to Antarctica because it's often there very cold, and the water in the Earth's atmosphere crystallizes out, and you get views almost like looking to space at, as said, 1% of the cost. Now, it's been the goal of people to get to the South Pole for over 100 years. And it was actually first reached just about 100 years ago. There were 2 teams competing to be the first human beings to go to the South Pole. The top team was a Norwegian team led by Roald Amundsen, who had just months earlier, before he set out for the South Pole, been beaten to go to the North Pole by another team, I think from Finland. And he turned around immediately and began an expedition to the South Pole. He learned from his voyage to employ hot new technology called dogs. And these dogs were a much more preferred technological solution than that employed by the British team. You see the British team's beasts of burden. Those are the other men in the expedition. The reason for that was really, it came down to a matter of taste, literally. So every animal that had gone to the South Pole or had tried to get to the South Pole had been eaten. And in fact, the Norwegian team ate the dogs that are shown there after they got to the South Pole. They beat, spoiler alert, they beat the British team by 3 weeks, only 3 weeks. And that 3-week difference made all the difference in the world for the British team. Unfortunately, they were much slower, they used more fuel, more food, and they ended up dying on the ice. And they're also sledding with them, carrying all the scientific equipment, whereas the Norwegians just went up there, plant the flag, come back. So this is what they saw when they got to the South Pole. They saw a Norwegian flag, and they could see it from over 2 kilometers away. Can you imagine like walking for, oh, what is that on the horizon there? Oh, it's a Norwegian flag, great. You know, whenever I talk to, my college kids about this, and I say, remember when men landed on the moon? They're like, what are you talking about? I'm 18 years old. But I have a feeling that many of you in the audience might have remembered when Neil Armstrong first set foot on the moon. Now imagine being the first to set foot on the moon, or so you think, and popping out of the Eagle and landing on a Russian flag, okay? There's a Soviet flag. Now, can you imagine the heartbreak? And I saw a lot of parallels between the quest to be first in exploration, in conquest, etc., and also to be first in scientific discovery and capture rewards and glory and namesakes and so forth, and be the first to do so. And so getting to Antarctica is still very dangerous, as this video, grainy as it is, shot during one of my last voyages there, depicts. You have to be, very, very serious around these penguins. They look really cute. They look like me in a penguin suit, okay? But they're kind of antisocial. So, So my kids always want me to bring back a penguin, but, I did on one voyage. I brought back a stuffed penguin, not a real stuffed penguin, an actual doll. So nowadays, a lovely place. When you go down there, you stay in a almost like a space station on a frozen plateau, an ice planet like Hoth, and you stay in a room that you can touch the walls of both sides simultaneously if you reach your arms out. But it's still better than what Scott and Amundsen had to go through 107 years ago. You take a selfie. You want to post to Instagram and Snapchat that you're there, and you get good internet coverage. You have no cell coverage, but you get internet coverage. And then you get to work, and here's the observatory in which BICEP was located. It's not the metallic thing. That's not a mirror. Remember, this is a refracting telescope. It focuses light using lenses. So that's not a mirror. That's actually a ground screen. We call it a ground screen because even the frigid can be down to 100 degrees below 0 Fahrenheit, and they love it when it gets down to 100 below 0 Fahrenheit because there's a sauna located in this building over here. There's actually a sauna which can be heated up to 212 degrees Fahrenheit. In the middle of winter, which is the middle of June at the South Pole, they go in the sauna, stay in the sauna for a few minutes, get nice and toasty, and then they run outside naked around the South Pole for about 5 seconds, and you can't wear any clothing or else you might get frostbitten where the sun shouldn't frostbite you. And that's the ceremonial, that's the axis on which the Earth is spinning. That little pole there is moved every year depending on how the ice is shifted throughout the past year. And so it's a phenomenal place to be, and we get somebody to actually live there. I don't go there for more than a few weeks. We actually get someone to live there and observe and tend to the telescope for a year. And we pay that person about $75,000. And usually to entice them to do it, I say, look, you just have to work for one night. That's all I'm asking. One night. You'd be surprised how well that works. So there's the observatory. I always say BICEP 2 is it's the second most important building at the South Pole. What's the first? Well, you gotta be, so that's the outhouse. Now, this is a picture you can only see if you've lived there for a whole year. This is sunrise in Antarctica. What's so interesting is you don't know which direction is east at the South Pole. It's not well defined. So sunrise is in the east, not always. They don't actually know where the sun is gonna rise or set each year. It's kind of cool, nice little fact. Well, lo and behold, on St. Patrick's Day 2014, Harvard University, we announced the detection of B-mode swirling twisting polarization, which is indicative of the presence of primordial waves of gravity, which themselves are indicative of an early explosive creation of the universe called inflation, which itself is indicative of the multiverse. Again, I'm going to keep saying that's the fifth great debate, the one we're still in the midst of. So we announced it, St. Patrick's Day. It wasn't because we had a lot to drink. We actually announced it, and we got a lot of great fanfare for this image here. This image shows the twisting, curling polarization vectors. So at each one of those lines, it depends on which axis would transmit the most microwave light. Not through polarized sunglasses, but through microwave sunglasses, if you like, the ones built in to the BICEP 2 detector. This is real data. Looks exactly like the ones I showed you before, the data I showed you earlier. So we got a lot of attention. Front page of the newspaper of record, the one that prints all the news that's fit to print. Yes, I'm talking about the San Diego Union Tribune. There I am, gazing heavenward, talking about a trillionth of a trillionth of a trillionth of a second. I like the bottom one, because it sounds like just some guy is watching, and he saw the start of the universe. Awesome, wow, boom, the Big Bang. And then up here, you see the space ripples on the front page of the New York Times. We were also featured on every television station. I'm sure many of you are old enough to remember. They tried to do live interview from the South Pole. We were long gone by then. So it made a lot of attention. And the most gratifying, the most satisfying thing as a scientist is to see your work featured in the most prestigious of all scientific journals. Of course, that's The Onion. What The Onion produced was a phenomenal headline. They actually convened top theoretical physicists and R&B singers. So there's Smokey Robinson, there's Aretha Franklin, late great, and Michio Kaku, who's a famous theoretical physicist. And underneath, you can't see it, says, panelists to discuss whether it's theoretically possible to give you my heart forever. And they talk about B-mode polarization. That's really cool. This actually happened. And it wasn't all to be. So soon after we published our results, we self-published our results without peer review on that March 17th day in 2014. We immediately got great congratulations, but also a great amount of skepticism and critique, which is natural and was expected. And in fact, we tried to preempt a lot of this with our discussion of how we came to reveal the data that we claimed we revealed. Remember, the stakes could not be higher. That day, I counted up, we were claimed in something like 10 different newspapers, instant Nobel Prize, and including some of the world's greatest physicists, like Lawrence Krauss, other physicists, saying this was the greatest discovery of all time, because it removed the need for a creator to produce the universe. And it meant that the multiverse was correct, the greatest sense. And then I read on another website, a Christian website called the Discovery website. It said, this is proof that God exists. So you couldn't have two more diametrically opposed things. Now, I like my friends that study planetary systems, like we heard, but I don't think they have debates about whether God, thinks about Pluto as a planet or not, okay? They have healthy egos, but I don't think they're as healthy as this. It showed to me the passion that cosmology unravels inside of people and really brings up. And I think it's unique in terms of all the sciences, and that's why I love doing it. But it was not all that it was meant to be. So soon after, we had criticism, and it's characterized here. It says, sure, it's beautiful, these two women cleaning some hotel room. It says, sure, it's beautiful, but I can't help thinking about all the interstellar dust out there. And we had thought about interstellar dust for a long time because interstellar dust is ubiquitous. And thank God it's ubiquitous because we are essentially made of interstellar dust in a way that I'll explain. So when a star of a certain age and a certain mass explodes, it sheds from its exterior all the elements that were made, starting with hydrogen, helium, oxygen, etc., all the way down to iron. When it tries to produce iron, it no longer produces enough thermal energy to prevent gravitational collapse that's trying to turn it into either a white dwarf, a neutron star, or perhaps, if it's massive enough, a black hole. When that happens, the star is called a core collapse supernova, explodes, rebounds, and spews the material that it's made of out into the surrounding system in the galaxy. So this must have happened in our galaxy, we believe, about 5 or 6 billion years ago, producing the matter through this process that I'm going to show here. So a star explodes, it tries to make iron, it explodes, it sprays out all that material into the interstellar medium. Some of it's hydrogen, and that hydrogen can then combine together and fuse and make helium. Helium, of course, was discovered not on Earth. First element not discovered on Earth, it was discovered on the sun. How do you go to the sun and do an experiment? They went at night. And by doing that, now they didn't actually go there, but they measured that there was something that looked like a heavy form of hydrogen, and that heavy form of hydrogen got the name helium, after the Greek god of the sun. So after everything congeals, you can ignite a new star, but you can also form planets. So what should the planets be made of? What should they have at their centers? Well, they might have rocky or solid cores made of iron. What is iron? If you've ever done an experiment, like the lecturer for whom this night is named after, Joseph Henry, what did he put inside of his inductance coil? He put a chunk of iron. That iron was once inside of a supernova that exploded. And you can get pieces of iron, and in fact, I'm going to give Larry a piece of iron in memory of being in honor of being the president on this 88th night, honoring the first president. And I brought with it a meteorite here, and what do you know about iron? It's magnetic. So I've got a magnet from the back of my badge, and you can suck it up. There you go. So this is space dust. It's just a giant form of it, but there's a huge distribution of space dust. Some is as small as molecules. Some is as big as a millimeter. Some is as big as a chunk, like the one that's in the Hayden Planetarium or the National Smithsonian Natural History Museum here in Washington. So some of these chunks are quite big. Some are small. Some went into the Earth's core. Some go into the crust. Eventually made its way into meat, made its way into something your mother ate, made its way into your bloodstream in the form of a hemoglobin molecule, which has iron within it. So we literally have remnants of a star. As Carl Sagan said, we are star stuff, flowing through our veins, the same stuff. So I'm not altogether upset about dust, because without it we wouldn't be here, but it caused a certain amount of consternation in our group. Because later it was found that what we had seen was not the birth pangs of the Big Bang, but we were confused, we were fooled, just like Hubble, Hoyle, Herschel, and Galileo, deceived by a dusty delusion, and saw basically what we and the whole world wanted to see. And we have made corrections to our approach, both the BICEP team, which I'm still a part of, and the new team that I'm going to describe in a few minutes, searching for and building upon the lessons learned from BICEP. So now we know that the universe is not this pristine, easily glimpsed depiction cartoon shown here, but instead is pretty darn smoggy, like Los Angeles on a typical afternoon. So along with our B modes being blown away in the dust, so did my Nobel Prize. I describe the kind of bittersweet feeling of being asked to nominate the person who should win the Nobel Prize the same year I arguably could have won it, but didn't. But so we learn from our mistakes, and that's the most important thing. If you don't learn from your mistakes, you have basically learned nothing. And so from us and the BICEP team and the new team that I'm going to talk about now, called the Simons Observatory, we're building on this. We didn't make a blunder. We didn't leave the lens cap on or say we detected something traveling faster than the speed of light or saw some aliens or whatever. We made a very, very exquisitely precise measurement of something that had never been measured before, and the way that we interpret it was wrong, and we had to retract that claim of interpretation. But the prize is still out there, and the real prize, which is the understanding of nature and its earliest secrets. So I'm the leader of this great team called the Simons Observatory, which is named after these men and women here, Jim and Marilyn Simons, and Mark Heising and Elizabeth Simons. And these two foundations have given us a quite generous amount of funding to construct an observatory in the Atacama Desert. Not at the South Pole, in the Atacama Desert. And one of the things that I least like about the Nobel Prize, you'll see from reading my book, is that it can only go to 3 people at most. And I say, I can't think of a single person on here, maybe me, that's not essential to the experiment that we're building. And so to give it to any one of us, should we prove successful, and that's always dangerous. What are you trying to see? What do you hope you see? Those are dangerous words when a scientist says that. So how does it work? It's actually the 40th anniversary of the most important invention for us parents, the dustbuster. Okay, it's 40 years old this year. And that's what we're doing. To get rid of the dust, we're building an enormous spacecraft to go out into the cosmos and suck up the dust and then take the dust. No, we're not doing that. That would be crazy. The only way we can get rid of dust is measure it with as many different microwave frequencies as possible. And to do that, we are relying on both the pristineness of the site where we're located, 17,000 feet in the Atacama Desert of northern Chile. We'll be located here. But also to measure different frequencies of the microwave sky, both looking for the effects of dust and dust alone, and then removing it from the combination of all the signals that we see, and hopefully what's left over will be dust-free for the first time, and that will then reveal this impressive list of scientific findings that we hope to see that are consistent with inflation, but don't prove inflation. And again, this could be not any higher in terms of our stakes. So we're observing over the next, starting in 2021, and I want to talk to you about the technology and what we're going to learn along the way, not only about the earliest moments in the universe potentially, but also everything that's happened along the way since the Big Bang to given photons that we see. And they interact with light and matter, and they get imprinted upon them the characteristic signature of their journeys. It's quite poetic. And so we're visualizing that in this little image here that shows both the microwaves from dust and the microwaves from the earliest moments in the universe, potentially. The way that we're approaching it technologically couldn't be bigger in terms of big science. BICEP was small, Galilean telescope sized. We're also building Galileo-like refracting telescopes, but we're also building an enormous telescope, a 6-meter diameter telescope that I'm going to show you next. So these are 3 small Galilean refracting telescopes. They're going to be combined with an enormous telescope, which is shown here, 6-meter diameter mirrors of a special design I can get into if people are interested. We're going to observe not at 1 frequency as BICEP did, but at 6 frequencies simultaneously in order to remove dust and also measure the cosmic microwave background, B-mode polarization. Here's where we're going to be located. There are neighboring experiments. Here's what the site is going to look like. And this is a huge endeavor. It's on all 7 continents at one time or another. We have scientists working on this project. Here's the big telescope. Light comes in from above, reflects off what's called the primary mirror to a secondary mirror, and then into a receiver, a cryogenic receiver, which is cooled down to 0.1 degree above absolute zero. It's big enough that you can use it for timeout for your bad grad students. So you can put your students in there. It's more than 2.5 meters across and more than the same high. And as I said, it has to be cooled down. This is an actual picture of the receiver being assembled outside of Boston. And so we're almost ready to start populating this thing in the lab, and then we're going to ship it down to Chile, drive it from sea level up to 17,000 feet. Inside of each one of the telescopes are refracting optical systems made of very high purity silicon. We use the fact that the semiconductor industry has spent trillions of dollars making high purity silicon. That makes it perfect for transmitting microwaves with very few deficiencies. They get also joined with these 3 small telescopes, we call small aperture telescopes, also cooled down to 0.1 Kelvin. These telescopes look primarily for the signatures of this inflationary B-mode primordial fluctuation that is theorized to exist. And here's one of the first ones that we're deploying to our lab in San Diego and a similar one in Princeton in the next week. So this is really exciting, unfolding right now, and really building on these titanic accomplishments of BICEP and that team's heroic work. The detectors are really magical detectors, and I'm getting to the point that Joseph Henry would be proud of, and that is the detectors can see microwaves of 2 different frequencies and 2 different polarizations simultaneously. And that makes them ideal for removing cosmic foregrounds like dust and also seeing the CMB. They have these fractal antennas, which I can discuss offline. We mount them in these detectors packages. We cool them down to 0.1 Kelvin. We observe for 5 years with this device. And then at the end of it, we're going to know much more about the properties of everything that happened in the universe's history since perhaps the first moments of its existence. So where would Joseph Henry come in here? Well, he comes in here. We have these inductors that you see there, and they're used in these very magical devices made of superconducting electronics. These are pieces of material called niobium and niobium titanium, which when cooled below their transition temperature, their critical temperature, superconduct and act as perfect conductors, which means they can be perfect inductors, which means that they can transduce and transform small voltages, make them into bigger voltages, or transform current into voltage as well. And he would be astonished to know we're doing this at a fraction of a Kelvin. It's just mind-bending how much the technology has improved. Here's the timeline. I'm going to finish up in a couple of minutes and leave time for thunderous applause and many questions. Here's what we're going to observe on the sky. If you could see microwaves, this is what you'd see. What I find so interesting, and we're going to target different regions and look at the data and cross-correlate it in many different ways. What tickles me is that 1,000 years before us, there were astronomers working in this region. They were called Incas. The Incan people were very adept and knowledgeable about the night sky. And what's so fascinating to me about the Incas, they didn't care so much about the constellations that we care about. They cared about these dust globules, these Bach globules that exist in the Milky Way galaxy. Unfortunately, we can't see from the northern hemisphere. But if you go to the southern hemisphere, if you go to Chile, if you go to Peru, where the Incas were prevalent, you will see these dusty constellations. So if you were an Inca living in 1200 AD, you would see a constellation that looked like this. And you'd ask somebody at a local bar, what's your sign? They'd say, I'm an umbilicus. What are you? Oh, I'm a bird. And that's how they noted what things were. Now, this is just dust clouds in the Milky Way galaxy. It's kind of poetic, but we're also looking for dust for very different reasons that perhaps they would not recognize nowadays. So I like to conclude these talks by saying, I'm not, the most biblical person in the world, but if you remember your Bible studies, and I don't care if you believe in the Bible or not, but if you look in your Bible, it says Adam means dust in Hebrew. It means he was created from the earth, remember? And then at the end, what does it say? Ashes to ashes, dust to dust. That means your whole life will culminate, eventually you'll dissolve and become part of the earth. So for me, it's very poetic. Your life is lived between these two punctuation marks that are both dust. And our job as human beings is to make the most of that brief window between two periods of dust. And I think it's very poetic, and I've come to love dust probably much as Carl Sagan, who took this image with the Voyager 1 spacecraft called the pale blue dot. He talked about the dust moat that is the earth on which every saint and sinner, every person you've ever heard of, and you, if you were alive when this selfie was taken in 1990, you are in this image. I see myself over there. Right? And you're just a dust. You're just a dust, or just a dust grain floating in space. So I want to leave you with that. And as I said, we are stardust, we are golden, and we can't get back to the garden unless we know more about dust. These are how the elements in your body were traced back to certain aspects of a supernova or star in our galaxy. And I want to conclude this discussion of the beginning of all things with a quote from that great astronomer, Winston Churchill, who said, "This is not the end. It is not even the beginning of the end, but it is the end, perhaps, of the beginning." So thank you very much.
Q&A.
Same here.
Yeah. So we have time for some questions. As many of you know, we have a procedure for questions. There are people with microphones. There's a red microphone, a blue microphone, and a black microphone. When the microphone, if you keep your hand up long enough and the microphone comes to you, and I point at you or call out the microphone color, please stand up, tell us your name, ask a question. No speeches. Save them for the social hour. Ask a question. And we'll proceed. One reason for this is so that the people who will watch the video later and the people who are watching now on the live stream can hear your questions. So we have, where's the blue mic? Where's the black mic? Black mic somewhere?
It's in the back.
Okay, and where's the red mic? Okay, blue mic, black mic, red mic.
My name is Scott Matthews. I am a member. Can you say something briefly about how these microwave measurements allow you to extract information about the mass hierarchy of neutrinos?
Very good. So there's a notion that neutrinos have mass, and that has been verified from what are called neutrino oscillation experiments. So neutrinos are the only one of the fundamental elementary particles. There's only 17 of them. They're the only particles for which we don't know their exact masses. And there's two different ways that their masses could be arranged. They have masses at least 1/millionth of the mass of the electron, about 1/millionth of the mass of the electron or lower. There's a lower limit on how massive the neutrino could be. That means it has to be more massive than about 50 millielectron volts. And there's two different ways you could organize what we know about neutrinos is that we know the difference in the squares of masses between the three different types of neutrinos. So there's two different ways you can permute these three different types of neutrinos. One is called the normal hierarchy, and one is called the inverted hierarchy. The inverted hierarchy has the more greater mass of the sum of the neutrinos. So we could actually measure those in the very, very near future if nature is kind and the neutrinos are actually in the inverted hierarchy. If not, we have to wait for experiments like the Simons Observatory or perhaps a space mission later in order to make a convincing that is greater than 5 sigma detection of the minimal mass splitting of the neutrinos, which is about 50 millielectron volts. So you have to get down to about 10 millielectron volts in order to make a definitive detection of the neutrinos if they're in the normal hierarchy, which most people expect they are. If not, they're in the inverted. That'll be easy to measure. So that could happen in the next year or two, actually.
Black microphone.
Yeah, I'm Joe Powers, and I'm not a member, but my question is also about neutrinos. What are the prospects for the direct measurement of the cosmic neutrino background and maybe seeing past this microwave background horizon?
Yeah, so it's said that, when all neutrino experimentalists get old in their lives, they always become infatuated with the cosmic neutrino background. So let me first say what that is. The CMB is the cosmic photon background. It's a background of light in the microwave region that started off its life, if you will, as ultraviolet light, maybe even gamma ray light, and then it got redshifted as the universe expanded. Neutrinos are not bosons, they're fermions, so they have different characteristics, quantum statistics. They are actually decoupled earlier from matter, so their actual thermodynamic temperature, they're described by a Fermi-Dirac distribution. That could be detected by which is a colder temperature. So instead of 2.7 Kelvin, they're about 1.9 Kelvin. Their density is comparable to the number of photons there are in the universe, but they interact something like 10 to the 40th power, 10 to the 40th times less strongly than do photons or electrons with one another. So they're incredibly difficult to detect. Some say they cannot be detected directly. In other words, a cosmic neutrino comes in your lab, hits your detector, and you detect it. There is an experiment at Princeton called Ptolemy, Princeton, Tritium, something. I'm not going to try to, I have my own troubles with acronyms, as you saw from BICEP. So they are attempting to measure aspects of the cosmic neutrino background directly. We're attempting to measure the mass of the neutrino, which you would then infer based on how large a density you ascribe to the cosmic neutrino background that you've detected it. And so it actually distorts what we call gravitational lensing and distorts the path and trajectory of photons by according to the mass of the neutrinos when summed.
So we have
Yep.
red and
Red.
then blue. So red, then blue.
Hi, I'm Stephen Mortellaro. I'm not a member. I was wondering if you could talk just a little bit more about why, if inflation were proven, it would compel the conclusion that we live in a multiverse.
Yeah, so the multiverse, according to the creators of the inflationary theory, generally ascribed Alan Guth as an inarguably creator of the inflationary theory, Andre Lindes. And so there's a phenomenon called eternal inflation, which seems to be concomitant with the simplest models of inflation that you might expect to be A, detectable, and B, plausible, just from Occam's razor perspective. Those things have eternal properties where you cannot turn off the inflaton. The inflaton turns off in our universe, if indeed it did take place, when it violates what's called the slow roll conditions, when the field traverses these super Planckian lengths in small amounts of time. That then decouples and forms the cosmic microwave background, the photons, the matter, et cetera, that are coupled to ordinary fields in our universe. If that process is not perfectly finely tuned, almost finely tuned to a part like 10 to the 100th, then inflation continues at some place in the universe, in the multiverse, outside the inflaton permeates all throughout in the entirety of space-time. So there's no way to turn it off. It's like a solid rocket booster. You just wait for it to burn out. In this case, those things can inflate permanently, and they can inflate superluminally, and they can inflate such that we can never detect them. Each island universe will be separated by an infinite amount of space between one another. So the multiverse is a consequence of the fact that inflation is so efficient at nucleating matter and energy as it's required and as it was found to be. Remember, it was a solution to how did the Big Bang bang. That's what started. It turns out it's really almost like it's an overachiever. It can't be stopped.
Blue microphone.
My name is Attila Avni. I'm not a member. Where did the energy come from before the Big Bang?
That is a very, very good question. Usually people preface that question by saying, I have a simple question for you. So there are many different theories that attempt to answer this question. They are potentially related to the multiverse, in that the universe could have had a universe that is parallel to ours in space and in time. In other words, the multiverse could have produced another universe that's nearby to us in some abstract space. Or it could be their chief alternative to the multiverse is called the cyclic cosmology. There's another type of cosmological model that posits that the multiverse, that the universe did not begin with inflation, that the universe began when the collapse of a preceding universe from before it. Now, in that case, you can answer the question. My favorite question to ask, and you and I, Attila, are allied scientists, because I always say the favorite question I like to ask God, if God exists, what happened on the Tuesday before the Big Bang? In the case of the cyclic universe, there is an answer to that question. In the case of inflation and a singular one unitary Big Bang, as Stephen Hawking said, asking the question what happened before the Big Bang is like asking what's north of the North Pole. But I always say we all know what's north of the North Pole: Santa Claus. So we actually don't know. It's a well-posed question in a bouncing or cyclic cosmology, and many of the most eminent cosmologists in history have proposed that. Sir Roger Penrose in Oxford, Paul Steinhardt at Princeton, and many, many others are working on alternatives to inflation. Remember, every solution creates another problem, and you hope that those problems keep us fully employed.
John
We're going to
Evans.
do a double blue, so you also had a question. Then we'll go black, then we'll go red.
Black and blue.
My name is Ty Avni. I am not a member. And my question is, what is the source of dark energy? Is our universe expanding into another universe if multiverse exists?
So there are, the first question, what is dark energy? We know a very little about dark matter. We know certain things that it can't be. We know certain things about its density and its energy properties and characteristics and its interaction strengths. We know almost nothing about what dark energy is. It's one of the most mysterious of all known things, and it's interesting that it pervades and dominates the mass energy budget of the universe. It seems to have properties very similar to the inflaton, in that it causes an acceleration. In the case of inflation, it lasts much, much shorter, but it's much more effective. It expands the universe by perhaps 30 orders of magnitude in a trillionth of a second. Nowadays, the universe is lumbering along, and the Hubble constant's increasing at a relatively benign rate, at least by inflationary standards. The question of whether or not we can ever collide with another universe is perhaps one of the only ways we could prove the existence of the multiverse. If we do collide with another universe, then there will be, if you imagine our universe is a sphere in terms of its last scattering surface or when we see things, if it interacts with another universe, those two spheres will cross over one another, and their boundary shared in common will be a circular pattern. So people have proposed that you can look for multiverses by looking for bruises, if you will, on the microwave background surface. People have searched for that and haven't seen it, but absence of evidence doesn't prove that the multiverse isn't true. But what we can do is Attila's question can be answered. In other words, you could rule out the bouncing universe. You can't rule out inflation. And so some people are questioning nowadays, including some of the founding fathers and mothers of inflation, whether or not inflation is actually science, because it predicts a multiverse which cannot be falsified. You cannot disprove it. And that's very different from the type of science that, say, my hero Galileo engaged in.
Black microphone.
John Evans, not a member. How do you know that the dust is the cause of the microwave polarization fluctuations you saw?
So what we do is we used higher frequency measurements. And what happens with dust is dust scatters away higher frequency light from the sun, which is why you see predominantly red light at sunset and sunrise. And the way that it scatters light is very frequency dependent. So short wavelengths get scattered very, very strongly. And if the dust has any kind of axial symmetry to it, like a cylinder, it will get aligned by the Milky Way's magnetic field and therefore will act as a polarizing filter. So you'll see a combination: reddening, intensity diminishing, and polarization. That's exactly what we see when we look at very high frequencies. Then you extrapolate from the highest frequencies at which there's no cosmological data within, and you use those as a new experiment, extrapolate to low frequencies, and from that you can remove the dust signal, and the signal that we saw with BICEP 2 is entirely consistent with being from dust.
Red microphone.
Hi, thanks for the great talk. My name is Liz Landau, not a member yet, will be. I actually covered your studies back in 2014, and I worked for CNN. And so I was part of the fascinated media corps that then had to, unfortunately, say what happened next. And I wondered if you could tell us a little bit more about what went into your thought process of coming out before peer review, and also what advice you'd give to other scientists about doing the same.
Yeah, so that was a very fraught and perilous time in my life because we knew that what we were seeing was so consistent with the very thing that we most wanted to see, and we knew that that would cause other scientists around the world, including our chief competitor, which is a spacecraft called Planck, which is a $1 billion satellite launched in 2009, whose leaders were claiming at the time that they could see the exact same signal that we could. In other words, if there was a cosmological B-mode signature produced by inflation, they were able to detect it, and they had, $1 billion going for them. Remember, I said it's 100 times more expensive to go to space, and they had 400 people working on the project, probably. And we started to ask them, would you share your data with us so that we can confirm or refute the hypothesis that what we're seeing is or is not dust? We actually thought it was dust for a long, long time. And they said they wouldn't. And so many of us, I'll just say me, because I don't want to speak for any of the other, I thought that meant that they were holding the ace of spades, that they knew that they were going to detect it. Of course, they're not going to share us with the data. So I was subject to confirmation bias, ironically, by my competitors, thinking that they were sitting on and refusing to share data with us so that they could scoop us. And that's exactly what happened with Penzias and Wilson. They scooped this team at Princeton, which actually was looking for the signal from the Big Bang, arguably. And so this was rich in our field of people very competitively seeking the signal, in part. In my case only, I can only speak for myself, I wanted to win the Nobel Prize, right? So this was something that motivated us. Nowadays, I feel much, much differently about it. I feel like it has some really negative consequences for science. So I would say that, at least in my case, it was motivated by the desire to get there first and beat the competition. And we knew that nobody else is going to repeat our experiments. No one's repeated our experiments since, except we worked with the Planck team in 2015, a year later, to rule out our own hypothesis. So we did the thing that the best scientists should do. You should even work with your competitors, your enemies in a certain sense, in order to get down and reveal what's true. Now, do I wish that we had not claimed the original claim in the beginning? Of course. But I think, that's the way that things happen in science. You do learn from these types of things. I always think it's interesting because we always have these front page headlines, CNN and New York Times. You never see, retraction of the discovery, on the front page of the New York Times. Maybe they should save some media budget for that. But actually, I think the best thing we should do, Liz, to be honest with you, so my brother's a lawyer. Maybe he's watching out there in TV land, YouTube land. And he had to take ethics classes as a lawyer. My best friend's a doctor. He had to take classes in medical ethics. Why don't we teach scientific ethics? Why don't we teach what happens when you're an assistant professor and you really want to get tenure at some really prestigious school and you have this phenomenal result that could be or could. How do you handle situations like that? There are precious few books and precious few tutorials and manuals how to actually act ethically as a scientist. Doesn't mean we're not ethical. It just means that we should adopt these best practices that have worked literally for hundreds of years in other fields. We have a lot to learn from these other fields.
I think we're at the blue. Where's the blue microphone?
I grab my water.
Hi, I'm Bob Baer. I'm a member. Could you say something about how your program relates to the LISA satellite program?
Yeah, so LISA is a proposed satellite which can best be described as an extension of LIGO to space, and that would separate the LIGO detectors by millions of kilometers instead of by 1,000 kilometers across the United States, and would be far more sensitive because it would be isolated from seismic variations of the Earth. What they're looking for is similar science to the science that LIGO has detected: black hole mergers, neutron stars, supernovae explosions, doing actual astronomy with a laser interferometer. Now, can they detect variations of space-time caused by inflation? Most people think no. The reason for that comes down to the fact that gravitational waves are like light. They're a form of radiation. When light travels through an expanding universe, its amplitude decreases and its frequency stretches out. And so those two factors cause the energy density of gravitational waves to decrease as the redshift to the fourth power. And so to try to do science today, which we call redshift 0, versus trying to measure the gravitational waves at redshift 1,000, is 1,000 to the 4th power harder, which is 1 trillion times harder. So it's very unlikely that LISA could detect these waves of gravity from inflation if indeed inflation took place.
Red, then blue.
Hello, this is Ram, not a member. Thanks for the great lecture. My question is if gravitational waves can be used to detect accurately detect the age of the universe, if that's possible, is there gravitational waves from a different frequency that's beyond the Big Bang that we can tell there is an existence of another source before the Big Bang? Do we have instrumentation that is sensitive enough to detect one before the Big Bang?
Well, that would depend on the existence of a universe before the Big Bang, which, as I said, Hawking said is impossible. Time itself began. Now, what we see is only what has had enough time to travel to the detectors and telescopes today over the 13.799 billion year history of the universe, of our observable universe. Now, what we're trying to do with the B-mode polarization BICEP and Simons Observatory is akin to, let's say I stand behind this screen and I snap my fingers. You can't see me snapping my fingers, but you can hear it. You're using a different type of radiation, if you will, to detect an event, an explosive event, like snapping my fingers. And what we're doing is using the CMB as like this screen, as like almost like an amplifier. So we can only go back to the existence of things snapping or the existence of the bang itself with this type of technique. There are people, Sir Roger Penrose and others, and Hawking himself at some level apparently, who believe that there are traces of what he used to call eons, or existing universes before ours, that would leave observable traces both in the form of black holes, which he called Hawking points, Penrose calls Hawking points, or some other phenomena related to BMOs, but not gravitational waves. So we think gravitational waves are a crisp, clean detection mechanism for the theory of inflationary produced perturbations.
You don't have to stand up.
Thank you. Carl Merrill, I'm a member. There's another individual who started an idea of multiverses who actually grew up in this area, Hugh Everett III.
Yes.
With his probability theories concerning quantum mechanics. So could you comment on that and any linkage between that and the multiverse?
Yeah, so Everettian quantum mechanics. A question about Hugh Everett, who postulated what's called many worlds formulation of quantum mechanics, which was a solution, a resolution to the measurement problem and avoiding collapse of a wave function, so that every moment in time, you can decide, and your wave function that describes you can bifurcate into the number of potential choices that you may have. So I might want to give Larry a big hug, but in some universe, I would do that. I would give him a big hug. Another universe, punch him. Right? No, I'm not going to do that. He's a lovely man. He's a lawyer, right? You got to be careful. So that's a quantum mechanical theory of the multiverse. There are some scientists, Max Tegmark at MIT, classifies the different levels of the multiverse, and he has 4 of them. And at the highest level, the 4th level, everything can be decomposed and it's sort of reductionist. He's saying every single thing, you are made of quantum mechanical particles. You only need 3 different quantum mechanical particles to make you up for electron and 3 different types of quarks. Well, if you can reduce quarks to their only properties are only mathematical, spin, mass, charge, things like that. So everything can be reduced mathematical numbers, and then that is another form of a multiverse. So yes, it is a multiverse in a certain sense. It's certainly not a multiverse in the cosmic sense that we can access, and perhaps as Attila asked about, can you access them by seeing collisions with other universes? That would maybe not be helpful. But there are quantum entanglement measurements where people are actively pursuing this very question.
I think we'll do 3 more questions. We've got a red back there, and then a blue up here, and then a black over there. Or let's do it red, blue. Let's red, black, blue.
Will Angel, not yet a member. If you weren't working on B-mode polarization, the cosmic background radiation at the Simons Observatory, what would you be working on? What are you excited about?
So yeah, another way to answer that question is to go into the multiverse and ask, what am I doing in that other universe? And for me, it's always something to do with science. So I actually had lunch with Adam Rees yesterday, who did win the, he asked me, well, what if you did win the Nobel Prize? Like, would you have quit your job? And I'm like, well, no. What I'm so interested in is answering as many puzzles and questions as I could possibly do within the skill set that I have, which is pretty narrow, but it's enabled me to, both provide full employment. I calculated recently, I've employed over 150 UCSD students, and that's about $1 million a year for the last 15 years I've been able to generate. And they go out and they create labs and become professors now. And I think I love teaching, and I love being able to communicate and influence scientists. One of my friends who influenced me is a Russian scientist named Alex Polnarev. Maybe he's out there in YouTube land. Although it's England, it's probably pretty early in the morning. And he taught me the word scientist in Russian, and I hope there's no Russian speakers here to refute this, means someone who was taught. It means a person who was taught, which means your job as a scientist is to be taught and to teach. And so I would continue teaching, continue doing research. I would be, more than happy to do this type of astronomy, for the rest of my life. So I'm very excited to be able to continue doing it now at the cutting edge.
Black microphone. Yeah, that's black microphone.
I'm Jim Griffin, and I'm a member. Do I have this thing on?
Yeah, I can hear you. I can
Okay.
repeat it.
I guess I'm very interested in your wonderful history of this scientific development, and I have to say, totally admiring of your approach to it, your management of it. It reminds me of a story that I heard maybe 20 or 30 years ago.
Question.
About the North Pole.
Let him, he's praising me. Let him keep going.
No, ask a question.
About the North Pole.
Yes.
And the discovery of the North Pole, which said when the National Geographic revealed the logs that the first guy did not get to the North Pole.
Yes.
And then our Admiral Byrd, who flew over it, didn't get there. And that the North Pole was first traversed perhaps by somebody in a snowmobile from a submarine.
Yes.
And I wonder if you have any comments on that as a reflection of scientific development.
I've heard that. The thing that it recalls to me is two things. Well, one, a couple of years ago, the Russian, I almost said the Soviets, sorry, Putin, don't come after me. The Russians sent a submarine to the ocean. So the North Pole, you should know if you don't, the North Pole is not on a continent. There's no continent like Antarctica. You go to Antarctica, you drill down through 9,500 feet of ice, you hit rock. And that rock is the continental shelf of Antarctica. You go down over to the North Pole in the winter, drill through the ice, you hit ocean, the Arctic Ocean. And so there is no land there, except the Russians said, let's go underneath and plant a flag at the bottom of the ocean where the North Geographic Pole is. And the reason they did that is because they believe if there are any mineral rights there, as they thought originally in Antarctica, there are mineral rights, but you're not allowed to use them. So now they have dominion over it, just as the US has dominion over the South Pole, except nobody treats the Russians in this case very seriously. But the South Pole, if we were to leave BICEP and the other 3 or 4 experiments behind, another country could legally, by the rights of maritime laws of the United Nations, could claim ownership of the South Pole. We own the South Pole. It's a point, so it's not that great. But no, we own it at the U.S., one of the 3 U.S. bases. So the funny thing to me is that when Amundsen beat Scott's team there, the first thing Scott did is anything that like a grade-grubbing freshman of mine would do, he tried to prove him wrong. He was off by 10 feet. We were really the first ones to get there, and they made very accurate measurements, and they showed that he was actually correct at the South Pole for the first time. So Amundsen did get it there, inarguably, and Scott ended up dying 3 months later, unfortunately.
Last question.
Robert Thompson, I am a member. My question is, what went wrong with the BICEP analysis procedure that you failed to account for the dusty foreground?
So I wouldn't say in the sense, as I say in the book, it really wasn't a blunder. There were blunders made in science. There was a claim of faster than light traveling neutrinos by the Opera experiment. That was traced to like a faulty coax cable that someone didn't put. But this wasn't that. We had data that no one had ever seen before. We measured, as I said, the Earth's temperature in Kelvin is about 300 degrees Kelvin. The signals that BICEP saw from dust that we originally thought were from these B modes from inflation, these B modes were at the level of tens of nanokelvin. So you're measuring things at like a part in a billion. From a place where the South Pole, as cold as it is overwhelmingly blowtorch bright. And we were able to measure this fantastically small signal. Where we went wrong is we only had one frequency. And our original plan was to detect something, and then if we detected it, we'd have time and go back and follow up at multiple frequencies, which is exactly what we're doing now. But the problem was back then, we knew Planck was hot on the tail. And actually, it turned out Planck never released the results on this data. They never detected it. They never were competition. Maybe they were posturing. Who knows? But we didn't know that at the time. The fog of war was very thick amongst us. And we were afraid we were engaged in this battle of survival, in my case, to win a Nobel Prize and be there first and to get this title of detecting the earliest evidence for the formation of the universe. So the stakes are really high, and it made me, I'll just say, overlook the fact, even though I was concerned about dust, we all were, that we had enough data to go forward. And I described the thought process behind that a lot more in detail in the book.
Well, thank you very much.
Thank you, Larry. What's that?
So in appreciation for coming here and giving us this lovely talk on the 88th Joseph Henry Lecture, I'd like to present you with a framed copy of the announcement of your talk, signed by all of the members of the General Committee on behalf of the membership, and a copy of the Volume 1 of the Washington Society, the Philosophical Society of Washington Bulletin from March 1871 to June 1874, signed by me on behalf of the membership.
Thank you very much.
Thank you. And before we go, just a few closing announcements. First of all, PSW, as you know, depends on members and sponsors. If you're not a member back there, hello, asking a question at every meeting, please join. If you are a member and have not paid your dues, please pay your dues. And if you have paid your dues, please consider an additional donation, sponsoring a lecture or a lecture series, and perhaps volunteering to help carry out the Society's activities. We're particularly interested right now in people who maybe have writing experience and people who are able to do video, or at least help us with our video efforts. It's easy enough to join. Go to the home page, click on the join button. This will behave, it's not behaving. It brings up the membership page. If you click on this link here, well, the one in the middle, there you go. It brings up the application for membership form, and you can just fill out the form and submit it. There's a dues payment that you need to do. If you're not admitted to membership, we'll refund the money. It's very unlikely because there are no IQ tests and there are no financial means tests. There's simply the test that if you want to join, you should be very interested in science. If you have any questions, please see our membership director, Lloyd Mitchell, if he's here. Here he is. Or our social media director, Ann McQueen, who's here too. It's worth noting that PSW lecture attendance is only part of PSW's audience. In fact, PSW reaches a growing worldwide audience. Videos on the PSW YouTube channel have been viewed over 250,000 times. The plant definition debate was viewed over 11,000 times in its first week. And it's dues, contributions, and sponsorships that make this possible. PSW is a nonprofit educational organization tax exempt under Section 501c3 of the Internal Revenue Code, and contributions are tax deductible to the extent permitted by law and the IRS. All PSW members in good standing can wear the PSW rosette, the blue one. If you wish to purchase one, they're $15, and you may do so at the rosette table in the back of the auditorium. Upcoming lectures. Unfortunately, this is the end of the spring 2019 lecture series. You keep posted on the fall lecture series. I can tell you a few things that we are hoping to have talks on. So the perennial hope of a talk on Venus may come to fruition. We hope that Ellen Stofan will give that talk. We expect to have a talk on robotics by the CEO and founder of a very prominent robotics company. We're hoping for a talk on Argo, which is the flotilla of autonomous sensors that's floating around in the South Pacific and is part of a I'm going to say a growing effort, something that's probably going to be exponential of our autonomous sensors of the environment and reporting back massive amounts of data and vastly changing our understanding of the Earth's dynamics. Hopefully we'll have the winner of the Dragonfly Caesar competition, which we had talks on in the fall, both on Caesar and on Dragonfly, and we're looking forward in the summer to find out who NASA chooses to fund, so we'll have them. And we're looking for a talk on quantum gravity by somebody from Johns Hopkins, on artificial intelligence chips. Some of you may have seen recently the black hole was imaged by a consortium, and we expect to have a talk on that. We're going to have a talk called Lifelike by a fellow from UCSD on making artificial life or something like it, and so on. So I'm just teasing you, but we will have some of those talks. I'd like to thank tonight's crew, Connor Nixon on camera, Jared McQueen, camera on IT, Ann McQueen, our chat boss, Cameo Lance, our room boss, Robin Taylor, our live stream director, Noah Block, our wrangler, and our red, blue, and black mic runners. And please also join me in thanking the members of the General Committee who ensure that the Society is well run and solvent and do all the work required to hold the Society's meetings and present these lectures. Vice President Mark Clampin, who snuck out. Corresponding Secretary Robin Taylor. Recording Secretary James Heelan, who Treasurer Brett Magaram, Member at Large Connor Nixon, Web and IT Director Jared McQueen on camera number 1, Social Media Director Ann McQueen, Membership Director Lloyd Mitchell, and President and Program Director, I don't know who that guy is. All right, the social hour ends at, I guess today, let's say 10:40, promptly. So please use the side exit to exit the building, and I will now accept a motion from a member for adjournment of the 2410th meeting of the Society and the Spring 2019 Lecture Series. All, don't have. Second? All members in favor? Aye. All members opposed? Meeting is adjourned to the social hour.